Right, in this video we're going to continue with our examples. So in number 5, A, we want to find the integral of dz on z, where C is the circle mod z equals to 1 traversed in the positive sense. We're going to give you an opportunity to do B. They got a circle mod z equals to 2, and then we're going to do C, and then we're going to give you an opportunity to do D again. So number 5A, we have got dz over z. We're evaluating this around the circle. Okay, so our integrand is a function 1 over z. Now this function we can see is going to be singular at the origin when z equals to 0, so we've got a singularity here. Then we are integrating around the unit circle. Okay, now Cauchy's integral theorem says if there are no singularities anywhere inside and along the contour, and the contour is simple closed, then the integral is going to be 0. But in this case, there is a singularity inside, so Cauchy's integral theorem does not apply, and whenever the integral does not apply, we have to integrate manually, as it were. So, well, we are going to write the equation of the contour in parametric form. Just going to do a generalization of the situation here, and then we're going to come back to this. Okay, so in general, if we have this circle z minus z naught is equal to r, so we know this is a circle centered at z naught with radius r. Okay, we need to derive a parametric equation for this thing. Okay, maybe it's going to be easier if we start with the one where z naught is equal to 0. Okay, so maybe let's start with this one. So this is centered at the origin, and the radius is r. Now we know we can write this in parametric form. It's going to be x equals to r cosine theta, y equals to r sine theta. However, z is equals to x plus iy, so this is going to be r cosine theta plus ir sine theta. This is going to be r cosine theta plus I sine theta, but this is simply re to the I theta. So we are saying if we got mod z equals to r, the parametric form of the equation of that circle is always going to be z equals to r e to the I theta. And now we can generalize. If the circle is centered at z naught, then there's going to be z minus z naught equals to re to the I theta. So going back to our equation there, we have got z equals mod z equals to 1. So the parametric equation is going to be z equals to e to the I theta. Then dz it's going to be I e to the I theta d theta. So this integral, if you write it in terms of the parametric equations, so the parametric equations have got theta as the variable, so dz is I e to the I theta, z is e to the I theta. So if you're going around the circle once, it's going to be 0 to 2 pi. Because we could do pi to, or negative pi to pi, that's still going to be one rotation around the circle. The e to the I theta is going to cancel out, so this thing is just going to be I into the integral from 0 to 2 pi. So this is just I theta 0 to 2 pi. So this is going to be 2 pi I, which of course is not equal to 0, as we suspected, because we've got a singularity inside the contour. Right, so that's part A. In part B, in part C, what you're going to do, part B. In part C, we're going to do the same thing along a square with these vertices. Now, of course, according to the independence of path, the integral of this thing along a circle, we can change this so long as it's still so long as the contour is still containing that singularity, should give us exactly the same answer because of the independence of path. So it could be this, it could be a bigger square, it could be a bigger circle, so long as it's a simple closed and it contains the same contour. So in part C, we got a circle, a square, where this is 1 plus I, this is 1 minus I, this is minus 1 plus I, this is minus I minus 1. So that is a square with these vertices here, 1 plus or minus I minus 1 plus or minus I. Okay, so so if we call this C1, this one C2, this one C3, and this one C4, then we're going to work through this thing out manually. So this is C, dz is dx plus I dy, this is x plus iy. C1 is the line y equals to 1. C2 is the line x equals to -1. This is y equals to -1. This is x equals 1. So we're going to do the integral along each of those. So let's start with C1. So we're going to have the integral. If y is 1, then dy is 0. So I'm going to go through this relatively quickly, because we've already done this type of thing in the last few videos. So dy is going to be 0 here. When we come across y here, we're going to plug in 1. So we're going to have dx over x plus I. And then x is going from 1 to -1. X is 1 here, and then x is -1 there. Now this is just, remember that I is a constant this is just ln of x plus I from 1 to negative 1. So if we plug in negative 1, it's going to be ln I minus 1 negative minus ln 1 plus I. Okay, just going to leave it there for C1. For C2, we said C2 is x is negative 1, so dx is going to be 0. So this term is going to be 0 here. We're just going to have I dy. So I dy, x is negative 1. We're going to have iy minus 1. And then y is going from 1 to negative 1. If we just divide everything by I here, then the numerator is just going to be dy. It's going to be dy. It's going to be plus I, because 1 over I is negative I. So then again, this is ln of y plus I from 1 to negative 1. When y is negative 1, this is going to be I minus 1. When y is 1, going to be 1 plus I. Okay, C2, C3, since the computations are similar, I'm just going to say C3, this is the integral we are going to get, and when we evaluate this, we get ln of 1 minus I minus ln minus 1 minus I. And then C4, we get this integral I dy iy plus 1. We evaluate, we get ln 1 minus I minus 1 minus I. And so the integral of dz over z around C, we're going to have to add all 4. Okay, they have got like terms. So like if you look at C1 and C2, okay, these two are the same, ln I minus 1, ln I minus 1. In fact, they're exactly the same, so when you add them, we're going to get 2 ln I minus 1 minus 2 ln 1 plus I. And then C4 and C3, again, they're exactly the same. We have got plus 2 ln 1 minus I minus 2 ln minus 1 minus I. Now, already mentioned, when we work with these, we just do the principal values. So all of them are going to have magnitude root 2. So the magnitudes are going to cancel out. Okay, but maybe let me just write them out. So it's going to be ln root 2 for this one, plus I minus 1 is in the second quadrant, so there's going to be 3I pi over 4. Then take away ln root 2 for this one. This one is in the first quadrant, so that's going to be pi over 4. And then plus again ln root 2, 1 minus I is in the fourth quadrant, this one, so that's going to be minus I pi over 4. Okay, then we are going to have take away again ln root 2 minus 1 minus I is in the third quadrant, so this is going to be minus 3I pi over 4. Okay, so this is what's going to happen. So then everything is multiplied by 2. Okay, so when we remove the brackets here, the ln 2 terms are going to cancel out, because so let's see, this one is plus, this one is minus, this one is plus, and this one is minus. Okay, so those will cancel out. So we're just going to have the either 3I pi over 4 or pi over I pi I over 4, plus or minus. So the first one is 3I pi over 4, then minus I pi over 4 is this one. This is plus, this is minus, so another minus pi I over 4. This is minus, so that becomes plus 3 pi I over 4. Okay, so they're all over 4. 3 and 3 is 6, minus 2 is 4, so it's going to be 4 pi I over 4. This is going to be 2 pi I, which is exactly the same as what we found along the unit circle. Okay, so we are going to give you the opportunity to work through the same integral around the circle of radius 2, and then in part D around the rectangle with vertices as specified there. So you can just pause the video, and then when you press play, then you can compare with our solutions. Right, in the case of part B, we got a circle with radius 2. So the one we did earlier was of radius 1. So this time we got a circle of radius 2 as our contour. Now, from what we've said, the circle of radius 2 gets the parameterization 2e to the I theta for its equation, which is what we have here. So dz is going to be 2ie to the I theta. If we substitute into this integral here, that's going to be our dz, that is z. 2 cancels out, e to the I theta cancels out. It's exactly the same integral as we had before, so it's going to work out to 2 pi I. Then for part C, we got contour, which is it's actually, yeah, it's a rectangle with vertices 1 plus I, 2 plus I, 2 minus I, 1 minus I. But remember, we are integrating 1 over z. 1 over z is singular only at the origin. So that means everywhere along this contour and inside 1 over z is analytic, and so the integral is going to be 0 because 1 over z is analytic inside. Inside a closed contour also includes the boundary of the contour. Okay,